have your slides uploaded to?
I'm just wondering if I could like duplicate the screen there so I could use the pointer because I have quite a lot of clicking to do.
Yeah. So I think this could this person with your slides.
Yes. Just before we begin.
Discuss. And go to presentation mode. So that's the left.
This one, right?
Right. So there. Yeah.
Right.
Yeah.
Okay. So I just have to point it.
Anyway.
This.
Anyway. So you can look at
That's
screen this way. There you go.
So I'm not sure if the laser pointer works.
Laser is not working.
Right. Oh,
Yeah.
we'll have to do. Well, good evening, everyone. It is truly a great honor for me to be here today. My name is Paxtian. I come from Mexico City, and I would like to welcome you to my presentation titled E-Textile-Based Fabrication of a Multifunctional Wearable Device Using Graphene Reduced Metal Oxide. I'd like to first introduce the project, the contents of this presentation, and a little bit more about who we are and who I am as a student. So I come from Mexico City, but I study in a university called Polytechnic University of the Valley of Mexico, which is located about 20 miles north of Mexico City. And I also come representing a small startup company. Oh, appreciate it, thank you. A small startup company called Applied Nanotechnology Institute, which is an alumni-founded startup company focusing on research projects using nanotechnology. So we also collaborate with a number of different universities across Mexico on projects like the one I'm presenting here today. We don't just focus on what I'm presenting. We work with a variety of applications such as biomaterials, electronics, drug delivery systems, and a variety of applications using nanotechnology, as well as some educational activities and research congresses, etc. So with that being said, I would like to get to the heart of the matter. And I would like to start with the concept of wearable technology. Now, I'm sure like some of you will have heard of this by now, but if you haven't, I'm going to use like the flagship representation of this technology, which are the infamous smartwatches, right? So we've all seen them, and we know it's more than just a watch, right? You expect it to have some features just beyond telling the time or just aesthetics in general. And I'm not referring to applications in the devices themselves, but the health monitoring aspect, right? You expect it to relay some sort of data to you in real time that it's in some way user friendly and non-invasive. So you don't have to go to great lengths to know what's going on with certain aspects of your body, right? And you also expect like some real-time data gathering to keep track of your health in general. So I use the Apple Watch here as an example, but it's just one representation of real-time data gathering that usually is applied in these devices. However, the problem we encounter, or the problem that we are actively trying to pursue, is the lack of flexibility and applications. So these devices, for example, use light-based techniques to sense your heart rate, for example, which is called photoplethysmography, in which you use a laser to deduce the change in volume in your blood veins, for example. But if we apply material science, if we use material science, we can actually get a wider range of benefits in these devices. One of which includes novel transduction techniques. What do I mean by transduction? The heart of this is energy conservation, right? So going from one kind of energy to another. One key example would be piezoelectricity, which is shown here, which is basically the translation, so to speak, from mechanical energy into an electrical pulse using the crystallographical properties of certain materials, which is not what we're using here, it's just an example. Another is a wider range of stimuli to be sensed, so you're not just limited to, for example, heart rate. This is a glucose sensor using sweat from the user and a data processing device in order to determine the glucose levels from sweat. So you cannot sense sweat with current wearable devices. This integrates some aspects of material science and into the detection or sensing of some stimuli. And the key aspect to be taken advantage of here is flexibility, right? So this device, as shown here in the picture, is clearly flexible. This is a humidity sensor integrated with some aspects of polymer science, material science, in order to detect in real time the changes in humidity relative humidity in the user's skin. So these are just examples, but what our approach is to have first of all, an accessible fabrication materials. One key point that I would like to mention here is that we unfortunately, in the university and in our startup company, we do not have a wide access to some resources. So one key aspect was to make use of what we have to synthesize a device that was capable of sensing body temperature, localized body temperature, not overall, and strain sensing properties like flexion movements. We also wanted to achieve some sort of electrical properties, optimal electrical properties, so that we can read certain stimuli in the device. And scalability and high throughput were some key objectives, like ease to fabricate and ease to carry to the large scale manufacturing, for example. And because of this, we chose textiles as our flexible substrate. Now, there are two kinds of textiles, so to speak, that are used in literature. The first ones are woven textiles, like the one you and I are wearing here today, which are just basically textile fibers knitted in a specific way, right? Sometimes called the warp and weft of textiles. We have like this complex matrix of intercalated textile fibers. But they're also non-woven, in which the fibers are basically synthesized through physical or chemical processes, in order to achieve some specific properties in the textile fibers. Because of the accessibility to certain equipment and reactants, we chose to stick with woven textiles because of their accessibility, and more specifically, we chose commercial textiles, like the large sheets of textiles that you can purchase in any store. We chose to work with those to see if we can functionalize them into sensing devices. So with this, we chose, because we wanted to sense body temperatures and strain. In a literature review, we saw that polyvinyl alcohol, which is also a thermoplastic, was used to sense strain properties and body temperature properties. Not exactly with woven textiles, it was used in non-woven and other types of polymer substrates. But when this kind of thermoplastic is exposed to a heat source, its individual monomers stretch in a way that it doesn't, it deforms the material, but in a way that we could, well, we wanted to functionalize it in a way that we could sense it as some sort of change in resistance. But in order to have resistance, you have to have an electrical flow, and to have that electrical flow, you need electrical properties. And so this is where the nanomaterials or nanotechnology comes in. We used graphene, not exactly graphene. Graphene is an amazing 2D material, which is an allotrope of a naturally occurring allotrope of carbon. They share an sp2 hybridization among carbon atoms, leaving one free orbital for electrons to flow through. That's what makes it an optimal electrical conductor. Unfortunately, synthesizing or obtaining graphene or fuel-aged graphene is complicated and expensive. So this goes against our objective of scalability and ease of access. There are other variants of graphene. One of interest is graphene oxide, which is just doesn't have, it's not as simple as having oxygen attached to the surface. These are actually a variety of functional groups attached that are placed on top of the, on top, so to speak. They are chemically bonded with the surface of graphene. Now this gives us the advantage of accessibility because there's a standardized method called Hommer's method to synthesize this device, which we'll get into. But it loses its electrical properties because the electrons cannot flow freely due to the presence of these chemical functional groups in the surface. And so with some reduction processes, we can actually achieve the version that we use, which is reduced graphene oxide. And you still have some presence of functional groups in the graphene sheets, but they are considerably lower as graphene oxide while maintaining these the desired electrical properties, and the techniques of reduction are actually quite simple. And so with this, we can design any textile or smart textile in this way, in which the basic layer are the textile fibers, which we chose nylon 66, because they are, textiles is a complicated world, and we chose nylon 66, cotton, and polyester due to the chemical affinity between some chemical functional groups in these textiles and reduced graphene oxide, the polyvinyl alcohol, and one final addition was activated charcoal, which is also an accessible material. It's an amorphous carbon material. It's not a nanomaterial, but it has this high surface area, and it actually improves the conductivity based on some works that were done using similar materials, such as pen ink, for example, which has some similar morphology, and well, it's also a carbon-based material actually, but with this, we hope that our device would send movement and temperature, thus giving it the multifunctionality that was described. So the methodology that we follow, this is the first method that I mentioned for synthesizing graphene oxide. So graphene in itself is just isolated layers of graphite. As you can see, if you were to zoom in on graphite powder, you would see many stacked layers of graphene, and our objective here is to separate them using chemical reactions. So if you place it in a solution with a strong acid or a reducing agent, often called, this forms a called graphene intercalation compound, which doesn't have any specific order. We're just using the dissolved ions to separate the layers. And then you add an oxidizing agent, such as potassium permanganate, in order to further, this forms the pristine graphene oxide. And after that, you have to purify the sheets, so to speak. You have to reduce the manganese ions, which are extremely oxidant. And when you add hydrogen peroxide and water, these ions, these excess ions are removed, and the functional groups are formed onto the surface of the graphene sheets. And then doing some purification techniques, filtering, washing cycles, and centrifugating, we get graphene oxide powder. This is the methodology we employed, so we tried to make it as simple and scalable as possible. So we started with a graphene oxide solution, and the whole process is dipping and coating, which is basically using adsorption forces to deposit materials onto the textiles. So we wanted reduced graphene oxide, and for this we used a solution with sodium borohydrate. Kind of the same thing happens here when some of the ions, when sodium borohydrate is diluted in water, actually rip off functional chemical groups of the graphene oxide coated textile, thus giving us more conductivity, as we'll later see. And then we functionalize the device by also dipping in solutions of PBA and activated charcoal, respectively, to give them the sensing properties that we wanted to. But this is very nice and all, but we need a way of sensing what's going on in the device. So we need a way to measure the resistance changes and to have them plotted in real time. And one viable solution we thought of was using printed circuit boards from the infamous Arduino developer. They are actually used in multiple wearable projects nowadays. And so this version, LilyPad, was actually the one that we chose to sense these changes in the device. And we employed a potential divided circuit that allows you to know the value of an unknown resistance with the value of a known resistance and in and out voltage values. So it's a simple way to obtain the changes in resistance. And for this, we measured like the average resistance. So you have to take into account, like when you flex the textile fibers, the resistance actually varies quite a lot. So we tried very hard to not move the textile and measure the resistance to get an average value of where the resistance sits. And then we replaced it with a with a common resistor into a very simple circuit in which we could manipulate the textile and see how the resistance behaved in real time. And now for the results that we obtained. This is how this is a small video, I don't know if you can see it, but this is us moving the device, and in the ohm meter here, you can actually see the resistance values changing in real time. So when we started with the pre-reduction, this is just with the graphene oxide deposited, the resistance was quite high, like above 2 mega ohms for all textiles. And this is the same value because the actual ohm meter would not register any more than that. So it is definitely above those values, but once we reduced it, added it to the reducing solution, it reduced 3 orders of magnitude into kilo ohms. So it's not ohms, but it's still a considerable addition of electrical properties to the device. Then when we added the PVA, the resistance actually increased for the case of cotton and polyester, but with nylon it pretty much remained the same. And then when we added the activated charcoal, the resistance of these two was pretty much unusable. We had to use nylon, which actually yielded some pretty unexpected results. So then we proceeded to characterize this device using infrared spectroscopy to determine what's chemically going on there, so to speak. So this peak here at around 3200 wave number corresponds to an hydroxyl peak, like this broad, strong peak present in graphene oxide, and the activated charcoal as well. But if you take a look at the nylon and functionalized nylon, especially the functionalized nylon, which is the green line, you'll see the absence of this peak, thus indicating that we removed some of the functional groups of the graphene sheets. But what's also very curious is that we have peaks corresponding to stretching of amide bonds here in around the 1700 wave number section in all materials. They were of different intensity and strength, but it was present nonetheless. Now this is how the device behaves. I don't know if it's kind of hard to see, I imagine, but as we stretch it in bending, the real-time resistance values actually change, they vary. So this gives us an indication of some functionality in the device. I would like to point out here that this is at its very early stages. We don't have the signal to noise ratio, as we'll see in a bit, is quite high. So this was more of a proof of concept that we can actually make commercial textiles functionalized into sensing devices, but we still have to figure out this part, because when we bend it, you can see some change in how the signal behaves, but this is somewhat unreadable still. We have these peaks, which are pretty much noise. This is the raw signal. I have not made any modifications to this. As well as when you twist it, we have like an average non-modified signal here, but it behaves erratically if we twist it in this way. So it produces a lot of noise, but it behaves differently nonetheless. And when we heat the device, we implemented a stepping method of increasing the temperature gradually in the span of about 8 seconds from 30 to 50 degrees. So we used a different heating magnetic stirring devices to have an actual reference to the temperature. And as you can see, it behaves quite erratically and unpredictably, but it's different from the other behaviors of twisting. So I'm gonna go into some challenges and perspectives we encountered here. And the first was the textile fiber quality, and this was to be expected because they were commercial. We did not have any control over our substrate, but we decided to work with them nonetheless. So this is a optical microscope picture of with a 40x lens of the nylon textile. This is not functionalized, it's a textile by itself. And as you can see, these are the individual fibers themselves, and they're separated by about spaces of an average size of 45 microns. So the fibers themselves are about 10 to 12 microns thick. And we actually observed something we dubbed anisotropic conductivity. We tried to find some term for it in the literature, but we couldn't find anything related to this, because the conductivity of the device actually changed differently or behaved differently depending on the direction you twisted it. So it was conductive in one direction, but in the other it wasn't, right? So that's why it was shown to only two behaviors, like twisting and bending, because in the other ones we did not exhibit any conductivity because of the morphology of the fibers themselves. Another one is the device exposure to environment. So a lot of external materials can be inserted here if the material is not protected, and this can affect the overall performance of it. Signal to noise ratio, as I mentioned, is still quite inefficient still, but it is pretty much a proof of concept what we did here, and a low sensitivity to temperature changes. So as if you saw, we increased the temperature up to 50 degrees Celsius, which is way above what our average body temperature is. So it's not as sensitive as we want it to be still. Some work to be done is to further characterize the device using electron microscopy to determine the morphology of the actual device. Another one is the encapsulation or protection of the device, the overall performance, the signal processing, And we're actually working on a computer simulation of the individual fibers once the materials were deposited to see how it behaves during the twisting and heating. And as we go further, the applications that we hope this device will have are with high-performance athletes in order to help them better check their health and their performance during a certain sport. For this, I would like to thank my advisors, Dr. Yosemite Leon and Elise Bravo, my amazing research team, and of course, Rice University for allowing me to be here, and Education USA for allowing me also to participate in this Congress. I am open to any questions you might have. Thank you very much.
Thank you. Do you have any questions here? All right, so if not, let's take a quick break. I'll be back at 2:30. And so for those who are going to present in the next session, it's a good idea to upload your talks